All right, so yeah, today I'm going to talk about not any of the things he listed, I guess, but about passwords. And we all know passwords really well. We use them every day. For the purpose of this talk, we'll think of a pretty simple setting, right, where you have a login server, maybe has hundreds of millions or even more accounts. People register a password, they log in at some point. Of course, real production password and authentication systems are much more complicated than what we're talking about today. There's all these soft machine learning-based tools for detecting if it seems like it's a fraudulent login. We have second factors and all of this type of stuff. We'll be glossing over those details. Just point out that all the stuff that we're talking about in the talk today is going to be relevant and work in conjunction with those types of tools. So we all hate passwords, right? They kind of suck. There's lots of problems with them. I'll just be focusing on a couple examples of things that are coming up with that our work is addressing. So one is obviously we need to deal with password database compromises. You know, a day doesn't go by when we hear about a new huge compromise. These are being used increasingly now. The prevalence of password data on the web is being used to fuel remote guessing attacks, so-called credential stuffing attacks that are one of the biggest sources of compromise these days. And then usability is a big pain, right? Memory errors, I always forget which password's which, typos, people have trouble typing particularly complicated passwords. And despite the potential for things like password managers, including things like built into Firefox, for dealing with this, they don't seem to yet be adopted quite widely. So we've been doing a lot of work on various aspects of all those problems. I'm just going to mostly touch upon two. One is this very recent work on understanding a generalization of credential stuffing attacks, what we've started calling credential tweaking attacks. And in addition, the first kind of defense that we're aware of proposed for dealing with this, something we're calling personalized password strength meters. And I think this is something that I'm hoping that will get widely deployed at some point soon. And then at the end, time allowing, I think I'll have time, we'll talk through some of our work on typo-tolerant password checking. So trying to deal with this particular usability issue of mistyping your password when you manually are entering it. Okay, so first part will be on the security issues. And definitely with security of passwords, it's like impossible to avoid seeing headlines. I guess this is the most recent one about Google having trouble with their plain text passwords. I guess the short answer to that question is that no, it doesn't really affect you in the end. I think they don't think there was actually any access to these passwords, but still indicative of how companies have been having a hard time ensuring that they have properly secured password storage. And then now the prevalence of these leaks is that you just get dumped on the web, on Pastebin or other parts of the so-called dark web, and there's just tons and tons of data out there that is being used in attacks. And so these types of headlines really speak to two of the more important threat models that come up with passwords. And I'll just go over each of these in turn. The first is this issue of server compromise. So had Google servers gone compromised with these plain text passwords, that would be a big problem, right? And so this motivates the need for password protections for storage. And right now that kind of takes two parts. The first is the use of slow hashing, salting plus slow hashing. So you take a cryptographic hash function like SHA-256, you choose a random salt per user account, and you hash this over and over again, right? And this is that's the kind of more traditional approach. Nowadays, we also have these memory hard hash functions as well, things like scrypt, argon2, which are being increasingly deployed that not only take longer to compute the hash, but also take up a bunch of memory when you're required to do that. These are really useful because they slow down cracking attacks, right? When you reach the server, you now have something like this that's stored in the server. You have access to the salts. It's a public function, so you can compute it as the attacker, but it takes you longer to compute each guess you might try against the password hash and therefore slows down the attacks. It doesn't prevent them, and so that's something that has motivated using even further storage protections, which are what I started calling back-end crypto servers. I think other people call them that as well. And the idea here is that we're going to basically have a split trust model, that we have a front-end like login service that actually is, has access directly to the password hash database, we're also going to have a separate system that has some type of secret cryptographic key. And whenever we're going to check a password, we now do a kind of interactive protocol, just a one round trip protocol to talk to that backend crypto service to help us compute what is now a secretly keyed hash. So, companies like Facebook and others, they use like just a keyed hash function like HMAC. You just think about this as something like SHA-256. But the point is now that if you get access to that login server and you get access to that database, you can't check password guesses now by yourself. You have to go talk to this server, someone who has this cryptographic key K. A bunch of years ago, we did some work on trying to improve these to like deal with various deficiencies of this HMAC approach, like the fact that you may want to rotate this key K from time period to time period, and it's hard to do if you're just using HMAC. And also to support like outsourcing this crypto service to third-party services that you don't necessarily want to trust, even with the hash of the password, which is how this HMAC system works, and support things like blinding. And that's a system we called Pythia. But I'm not going to talk about it in more detail. Okay, so that's the first kind of important threat model, and we have some pretty good approaches for helping deal with those types of issues. The second big issue is a threat model is remote guessing attacks, right? And here you have some person on the internet who is sending guesses against particular accounts to the login service. They typically have a restriction, how many guesses you can make before something should be flagged by the web login servers. So you have some type of lockout threshold, maybe 1,000 or better yet, like 10 or 100 before this account gets locked and you notify the user that something's wrong. So this may seem good because we only get a few guesses, right? And even with the bad passwords people pick, maybe locking someone out after 10 guesses is fine. But increasingly what attackers are doing is taking advantage of leaked data and mounting what are called credential stuffing attacks. So remember, there's like billions and billions of users' passwords that are now available for anyone to go download. And so you get a big list of people's passwords. In fact, my password, which was not password 1, but was something equally bad from like 20 years ago, is in this 4IQ database. And also explains like why my Skype account got hacked a few years ago. Very embarrassing. You can ask me about it later. So anyway, you go grab this database, and what do? You just try log in Tom at this particular service, and you try the password that's in the database. And this works surprisingly well. Simulations suggest that 40% of the time this is going to work. If your username's in the breach, with almost half the time, that password's the right one. And why? Because people reuse passwords across sites, right? That's what all the measurement studies indicate. And there's some industry reports suggesting that actually the majority of account compromise, remote account compromise, is because of credential stuffing these days. So that's motivated a move to a defense, which I'll just call credential stuffing countermeasure or breach notification service, where basically now the login server is going to get information about when their users end up in a breach. Okay? They could go download actually these dumps themselves. You can pay companies now to give you a notification if one of your users ends up in a breach. And when they see that Tom password 1 ends up in a breach, they'll say, hey Tom, go reset your password. Okay? And this should prevent at least the credential stuffing kind of attack. What it doesn't prevent is, and then I'll go and actually change my password because they're forcing me to, and maybe they restrict me from choosing my old password. This is exactly how Cornell does it, for example. And I'll pick some new password. Password 2? Well, yeah, maybe you didn't see the animation, but I went from password 1 to password 123, which will be very important, so thank you. So now this attack doesn't work, but the obvious thing an attacker can try now is exactly kind of iterations. Oh, before I get into that, I'm sorry. This is such an important thing now that you actually see a bunch of services that are trying to make this very easy to access breach notification. So Have I Been Pwned, if you've heard of that, is this service that Cloudflare now operates in collaboration with Troy Hunt to check if passwords are in a breach. And then Google just released an extension a few months ago for doing password checkup. And basically these are trying to do secure protocols for these type of checkups. And we have some work on kind of in this space as well that you can ask me about later. Right. So what can an attacker do to adapt to these countermeasures? Well, they can do what we started calling credential tweaking attacks, which is exactly this idea that maybe users are choosing very slight variants of the things that are in breaches, and I could just try, hey, maybe capital P password. Oh, maybe I'll try adding a 2 and 3 on the end, and sure enough, this will compromise in just a few guesses, less than the threshold before an account lockout occurs. So I should say I don't know if there's any evidence that attackers have really started doing this in bulk. I think credential stuffing still works in a lot of contexts. They're kind of sticking with that. We don't know. I don't know if they're using these or not in the wild. There hasn't been any evidence of this. It'd be a good measurement study target. But there have been some academic works kind of indicating that, at least in simulation, this is going to definitely be effective. And you can kind of see immediately once you get some data about how people pick passwords, there's going to be similarities. You can kind of generate some mangling rules for generating guesses given someone's breached password. And I should also say there doesn't seem to be any defenses that have really been discussed much in literature beyond kind of checking based on trying to do an attack. So we started tackling this from the point of view of trying to understand both how bad attacks can get, credential tweaking attacks, and also how we can prevent them. And the unifying theme underlying it all is a kind of data-driven approach where we're trying to learn password similarity models. So we started also by grabbing this breach data, which is, like I said, publicly available, and it's huge, right? There's 1.4 billion email password pairs. There's about 1 billion unique emails in it, lots of passwords. There's a lot of lot of usernames in this that have multiple passwords, right? And this is useful for us because what we actually have from this breach database is something more like this, where you see that maybe I have password 1, I also have Cornell Tech yay, exclamation point, and other people have other passwords. And you can start seeing patterns already, right? If you just start doing simple checks like, oh, how close in edit distance are people's passwords, like a lot of people are picking very similar passwords, right? So for example, in this, you can see that other people you can see this pattern of replacing a 1 with a 1, 2, 3 at the end, and this is how we're going to start getting some glimpse of how to build mangling type rules. We want to take a data-driven approach. We didn't want to sort through this manually or semi-manually, and instead just threw machine learning at it, essentially. Because this ends up being a very nice natural language processing type problem since these are human-chosen passwords. So what we want to do in the end is train a conditional, basically an estimate of a conditional probability distribution, like probability of W prime, like a new password, given some old password W. This is the thing that's in the breach. And we want to be able to do that for all the W's that we see out there. And if we get such a good kind of estimate of this password similarity model, this ends up giving us a good credential tweaking attack because you can basically stick in the breach password and with a little bit of work, enumerate a bunch of passwords in probability order under this good conditional probability distribution. There is some work to do here, but it's not too bad. Okay, so we want to do that, so we started exploring how to build such good password similarity models. And there's a lot of machine learning techniques built for this. If you're familiar with machine translation type tasks, it's kind of similar to that type of task. And so we started with that literature. And at the end, you end up wanting to use something like a recurrent neural network encoder-decoder architecture, where you kind of stick something in, it converts a password into some vector representation of it, kind of encodes some information that's relevant to the learning. And then from that, you can decode to generate things that are correlated with this password. The most obvious approaches of applying things like sequence to sequence, which is a classic approach from the machine learning world, didn't quite work very well. They didn't outperform the previous attacks in this space. We had to do a bit of feature engineering kind of type stuff to make this work. In the end, we ended up with a system we called pass to path, which instead of actually just outputting character by character password at the other end, you actually output differences with the password W to get W prime. Turns out this I think helped the system better kind of focus on the mangling kind of things and learning those patterns. But I think many other people have no good intuition about why deep learning works very well. This empirically outperformed past other approaches. So in the end, this ends up being pretty big. It took a couple days on a pretty well-stocked machine. It's large. It's kind of a clunky model, which will become relevant for some other stuff in a minute. But it works. You can generate at least guesses for things we would care about in the remote guessing attack world, like thousands of guesses in milliseconds. So we did a bunch of work to show via simulations, splitting up a lot of data into test and train sets and kind of showing via simulation that this outperforms prior attacks and does a good job cracking passwords. We also were able to partner with Cornell IT to do an actual audit of the Cornell accounts. And this was exciting because it was really the first kind of actual real-world investigation of how well credential tweaking can work. So Cornell is actually, I guess, a mid-sized business in some sense. We have hundreds of thousands of accounts. We do use a breach notification service. So things that end up in breaches end up getting reset. And we have some various password requirements and stuff that required some customization of our machine learning. We spent a lot of energy to try and make this a safe experiment. Getting access to passwords is not good, even password hashes. So we actually went up to Ithaca, because we're based in New York City, to go do this in the presence of the IT engineers, and they were mediating all of our access to the password hashes. So it's a picture of us working up there. It was a lot of fun, actually. In the end, so there's about 15,000 of these accounts are actually in the 4IQ data leak, and so then we basically generated guesses based on the passwords that were in the breach data set for those, and we're able to compromise of those 15,000 about 8.4% in less than 1,000 guesses, which is actually the quota for Cornell. And so then we put these 1,300 or so accounts on a watch list so we could protect them better. And as I mentioned, this is the kind of first real-world evaluation of credential tweaking compared to the simulation-based approaches that people have done before. So it's definitely a problem in the sense that we worry that if attackers start using these types of techniques, they're going to have some success, right? And so we wanted to understand how to do defenses. Obviously, we can do these types of audits, but these audits are expensive, right? We had to go up to Ithaca, at least cost some bus tickets. They could do it themselves, I guess, but it's a lot of computational power to do these types of audits, and we might want to build new approaches that kind of work better in the workflow for password handling that don't require special cracking experiments. And so in particular, if we go back to this view, when you get a breach notification about my password being in this breach, we might like to try to steer users away from picking something that's going to be crackable in this type of credential tweaking attack. And so this led us to this idea of what we started calling a personalized password strength meter. So basically trying to take into account these breached passwords, these passwords that have been publicly breached when giving a strength score to users. So the starting point for this is a regular strength meter. So you've probably seen strength meters on many sites now, like things like ZXCVBN, which is a bit of a mouthful. They take in a password, give you a score, right? Maybe a 1 through 5 or a 0 through 4 kind of score. So we want to do this and just add the ability to take as input some prior breached passwords and take that into account, right? And intuitively what we want to do is say, okay, if password 123 is too close to this breached password, password 1, we should give it a low score. And there's lots of, you could imagine other kind of contexts, but here we're really thinking about these old passwords being the ones that are from a breach. So the approach for this, again, we use machine learning for it, and we, in particular, train what's a variant of a word embedding, but for passwords, so we uncreatively call it a password embedding, which is basically a function that maps passwords down to some vector representation. And you learn in a way that kind of preserves semantic similarities. It's a very classic, well-understood technique from the machine learning NLP communities. The point is that you can just take this embedding, run it on 2 passwords, and then take a dot product of the resultant vectors. And if that dot product is smaller than a threshold, then you get a good sense that this is very similar. And specifically, we built something based on fast text, which is a well-known algorithm. And this helps a lot. So first off, it's really pretty simple. At the end of the day, these embeddings just are a kind of lookup table that you can use. It's like 3 megabytes or so it's even small enough to, after we did some compression stuff, to deploy on the client side if you want to deploy it there. We combine it with a regular strength meter like CXVBN because we also want to just have an all-in-one kind of strength meter solution. And for example, it marked all of the, when we did our experiments, we also checked this embedding-based defense, and it would have marked all of the path-to-path vulnerable Cornell passwords as trivially weak, despite the fact that we're using kind of different machine learning approaches. I should definitely say we have not yet done any proper usability studies. I guess there's a lot of questions about like how a user would react if you kind of told them things are too close to something else. Okay, so that was the first part, and the second part, don't worry, is not 20 minutes long, so I'll be finished before the top. But that was focusing specifically on security issues and these kind of like targeted attacks specifically. And I'm hoping that these tools like the embeddings-based personalized password strength meters are something that we'll be able to deploy in various places to help improve security. So what I'll do in the time range is mention briefly some of this work we've been doing now for a bunch of years on typo-tolerant password checking, which is trying to improve usability for passwords. So the starting point for this work for me, was pretty much that I can't type my password very well. My password is not password one, and I like mistype my password a lot. In fact, when we did measurements later, I mistyped my password like a scary amount of time, like 35% of the time. And so at some point I got on this mission like, hey, wouldn't it be great if we could fix it so that I don't have to keep retyping my password? I could have chosen a different password, I guess, but I was very stubborn. But I'm not the only person who's had problems with this. And in fact, Facebook and some other companies actually for a long time now, this is like a 2011 article, have been tolerant of mistakes in typos in passwords. So, for example, Facebook would accept password 1, the correct password, or also two variants of it, capital P password 1 and all caps password 1. And the capital P password 1 was really important, I think, when they first deployed their app on mobile, because mobile keyboards were always automatically capitalizing the first character of passwords when they're deployed, and so this was an easy fix for that. But this raises this broader question of like, is this secure? Like, what other typos should we be trying to tolerate? This type of thing. And really leads into this question of how we can study typo-tolerant password checking, right? So we've been doing a lot of work over the years on this. We kind of did the first big measurement studies. Facebook clearly had done something internally, but didn't report on it. So we did a first measurement study. I'll briefly mention something about that. Looked at new cryptographic instructions. I won't talk about that. And then I'll just explain what the solution that finally solved my problem, which is this idea of a personalized typo-tolerant password checking system. And I'll explain that in a moment. So the approach that Facebook is using, and is kind of the natural approach, is what we started calling relaxed checking. And the complexity here is we're not storing passwords in the clear, right? If you got in an incorrect password 1, and just hash it, it's just some random looking string that's unrelated to the hash that's in the database. And so there's a question, how can you actually then check? We don't want to just accept any possible string that someone sends in. That would be too permissive. We want to check something that's close. But there's an easy solution if you have just a handful of types of typos that you care about, and that's this relaxed checking approach. Basically, you check the password as submitted. This won't work. It'll be some other random string. Then you apply what we call a corrector, right? So say we apply a caps lock corrector to the password that was submitted. We just flip the case of all the passwords, of all the characters in the password, and then rehash it, okay? And then check, is this matching the thing that's in the database? We can do that again and again with other characters. Maybe we just change various things, and finally get the right password because we hit the right corrector, okay? And that means that we get the same hash, and we're good to go. This is really nice because it actually doesn't require any changes to the database. You just use the same hashing system, and you just have to add some extra code to, like, while you have that password in memory on the web server, you just check it a couple more times, right? It does have the downside that if you want to make G sub k really slow, like we said before, you may have some performance issues. You may have to make the time to compute that take into account the number of corrections you need to do if you want to hit a certain level of latency. It's interesting, this actually, like I said, works with existing password hardening schemes, doesn't change what's stored, and in some of our initial simulation work, if you set the number of correctors pretty small, so the total number of things you check is 4, say, like in this example, that actually hits like 20% of the typos that people seem to make in Mechanical Turk studies. So that was pretty surprising, but I guess a lot of people make caps lock errors, for example, and also capitalization errors. We wanted to see if this is true in the real world, and we partnered with Dropbox to do a measurement study of their authentication infrastructure. It was really cool collaboration from my perspective to measure what this impact would be. So we basically instrumented to do this type of typo-tolerant password authentication, but we didn't actually change the authentication policy. We just checked if it would have worked and then recorded some anonymous statistics about that. I should say we didn't do anything. They did all that, and we just talked to them about it. We didn't touch any of their code. Collaborators did that. But it was pretty surprising. Like in a 24-hour run where we gathered this data, about 3% of all of the people who tried to log in failed because of just the most popular top 3 typos, like the ones I showed on the previous slide, these type of capitalization errors. And by failed to log in, I mean they came, they tried to log in, they had that typo, they left, and didn't log in again in that 24-hour period. And about 20% of users would have saved at least about a minute of login time if we had done typo tolerance, right? And so in the end, aggregated over the hundreds and hundreds of millions of users, this would have saved several person months, or would have added several person months of login time every day to Dropbox, which for companies that are engagement driven, this is actually this is like money, right? And so you can see why Facebook was probably very excited to turn this on. The more subtle issue is whether security degrades. I don't have time to go into the details, and you can talk to me afterwards or see the papers on it. But the high level bit is that the security actually doesn't degrade if you choose these things carefully. Okay, and then lastly, we wanted to, that type of relaxed checking approach didn't fix the typo that I always have. It's some transposition error in the middle of my passphrase. And so I wasn't satisfied yet, so we had to go on to do more work. And we came up with this idea of what we started calling personalized typo-tolerant checking, which I'll just now briefly explain. And the idea is that at a high level, we just want to learn. We have a system that's stateful, and we're going to learn over time the particular typos that a particular user makes, and we're going to do that as we proceed. So say I mistype and do password 1. Well, what we like to do is something like this. We're going to just cache. We're going to check to see if it is correct, and it's not. And so we're just going to add it to a wait list of recent kind of incorrect password submissions. Okay? And then I'm going to get frustrated. That'll get added as well. And then finally, I log in correctly. At that point, we can check that password 1 and this previously incorrect submitted thing, capital P password 1, are very similar. And they satisfy some typo policy. And so we can just add that now under a new salted hash to a set of what we call a typo cache. And we basically then, from then on, can allow submissions of that typoed version to succeed in login by checking both of the hashes. So there's an obvious problem with this approach, as I described it, which is that we are in for a while storing in clear these waitlist passwords, and we can't do that for security reasons. And so we did some work to figure out how to basically avoid ever storing anything in the clear. At a high level, the idea is we are going to use some public key encryption, and we're going to encrypt this waitlist under a public key. The secret key is then encrypted under the passwords that we are allowing login under. And so the final data structure looks something like this. Nothing is ever stored in the clear. When you go to log in, you check the hash. If it succeeds, you actually also can rederive the decryption of SK and then decrypt the waitlist in clear and check things out. But there's lots of details. Turns out this did fix my error. That was great. It also turns out to be secure. There's a bunch of theorems and statements in the paper. I'm just going to gloss over this. The high-level bit is that this doesn't actually degrade security, despite the fact that we've added some other values to the stored list. There's an open source implementation of this. It works. I'm using it on my laptop right now. I finally solved my problem, long story short. And with that, I guess I'll just stop and take questions. Yeah, thank you very much.